Semiconductor devices are electronic components that exploit the electronic properties of semiconductor materials, principally silicon, germanium, and gallium arsenide, as well as organic semiconductors. Semiconductor devices have replaced thermionic devices in most applications. They use electronic conduction in the solid state as opposed to the gaseous state or thermionic emission in a high vacuum. Semiconductor devices are manufactured both as single discrete devices and as integrated circuits, which consist of a number from a few to billions of devices manufactured and interconnected on a single semiconductor substrate, or wafer. Semiconductor materials are useful because their behavior can be easily manipulated by the addition of impurities, known as doping. Semiconductor conductivity can be controlled by introduction of an electric or magnetic field, by exposure to light or heat, or by mechanical deformation of a doped monocrystalline grid. Thus, semiconductors can make excellent sensors. Current conduction in a semiconductor occurs via mobile or free electrons and holes, collectively known as charge carriers. Doping a semiconductor such as silicon with a small amount of impurity atoms, such as phosphorus or boron, greatly increases the number of free electrons or holes within the semiconductor. When a doped semiconductor contains excess holes it is called p-type, and when it contains excess free electrons it is known as n-type, where P or N is the sign of the charge of the majority mobile charge carriers. The semiconductor material used in devices is doped under highly controlled conditions in a fabrication facility, or fab, to precisely control the location and concentration of P and N-type dopants. The junctions which form where N-type and P-type semiconductors join together are called P-N junctions. Diode. The diode is a device made from a single P-N junction. At the junction of a P-type and an N-type semiconductor there forms a region called the depletion region which blocks current conduction from the N-type region to the P-type region, but allows current to conduct from the P-type region to the N-type region. Thus, when the device is forward biased, with the P side at higher electric potential, the diode conducts current easily. But the current is very small when the diode is reverse biased. Exposing a semiconductor to light can generate electron-hole pairs, which increases the number of free carriers and its conductivity. Diodes optimized to take advantage of this phenomenon are known as photodiodes. Compound semiconductor diodes can also be used to generate light, as in light-emitting diodes and laser diodes. Transistor. Bipolar junction transistors are formed from two P-N junctions, in either Na-P-N or P-Na-P configuration. The middle, or base, region between the junctions is typically very narrow. The other regions, and their associated terminals, are known as the emitter and the collector. A small current injected through the junction between the base and the emitter changes the properties of the base collector junction so that it can conduct current even though it is reverse biased. This creates a much larger current between the collector and emitter, controlled by the base emitter current. Another type of transistor, a field effect transistor, operates on the principle that semiconductor conductivity can be increased or decreased by the presence of an electric field. An electric field can increase the number of free electrons and holes in a semiconductor, thereby changing its conductivity. The field may be applied by a reverse-biased P-N junction, forming a junction field effect transistor, or by an electrode isolated from the bulk material by an oxide layer, forming a metal-oxide semiconductor field effect transistor. The MOSFET, a solid-state device, is the most used semiconductor device today. The gate electrode is charged to produce an electric field that controls the conductivity of a channel between two terminals, called the source and drain. Depending on the type of carrier in the channel, the device may be an N-channel or a P-channel MOSFET. Although the MOSFET is named in part for its metal gate, in modern devices polysilicon is typically used instead. Semiconductor device materials. By far, silicon is the most widely used material in semiconductor devices. Its combination of low raw material cost, relatively simple processing, and a useful temperature range make it currently the best compromise among the various competing materials. Silicon used in semiconductor device manufacturing is currently fabricated into boules that are large enough in diameter to allow the production of 300 ohm wafers. Germanium was a widely used early semiconductor material, but its thermal sensitivity makes it less useful than silicon. Today, germanium is often alloyed with silicon for use in very high-speed CGE devices. IBM is a major producer of such devices. Gallium arsenide is also widely used in high-speed devices, but so far, it has been difficult to form large-diameter boules of this material, limiting the wafer diameter to sizes significantly smaller than silicon wafers, thus making mass production of GAAs devices significantly more expensive than silicon. Other less common materials are also in use or under investigation. Silicon carbide has found some application as the raw material for blue light-emitting diodes and is being investigated for use in semiconductor devices that could withstand very high operating temperatures and environments with the presence of significant levels of ionizing radiation. Input diodes have also been fabricated from SiC. Various indium compounds are also being used in LEDs and solid-state laser diodes. Selenium sulfide is being studied in the manufacture of photovoltaic solar cells. The most common use for organic semiconductors is organic light-emitting diodes. List of common semiconductor devices. Two-terminal devices, DIAC, diode, GaN diode, input diode, laser diode, light-emitting diode, photocell, pin diode, Schottky diode, solar cell, tunnel diode, VCSEL. VCSEL, Zener diode, three-terminal devices, bipolar transistor, Darlington transistor, field effect transistor, insulated gate bipolar transistor, silicon-controlled rectifier, thyristor, TRIAC, unijunction transistor, four-terminal devices, Hall effect sensor, multi-terminal devices, integrated circuit, charge-coupled device, microprocessor, random access memory, read-only memory, semiconductor device applications. All transistor types can be used as the building blocks of logic gates, which are fundamental in the design of digital circuits. In digital circuits like microprocessors, transistors act as on-off switches. In the MOSFET, for instance, the voltage applied to the gate determines whether the switch is on or off. Transistors used for analog circuits do not act as on-off switches. Rather, they respond to a continuous range of inputs with a continuous range of outputs. Common analog circuits include amplifiers and oscillators. Circuits that interface or translate between digital circuits and analog circuits are known as mixed-signal circuits. Power semiconductor devices are discrete devices or integrated circuits intended for high current or high voltage applications. Power integrated circuits combine IC technology with power semiconductor technology. These are sometimes referred to as smart power devices. Several companies specialize in manufacturing power semiconductors. Component identifiers, the type designators of semiconductor devices, are often manufacturer-specific. Nevertheless, there have been attempts at creating standards for type codes, and a subset of devices follow those. For discrete devices, for example, there are three standards: JEDEC JESD 370B in United States, Pro Electron in Europe, and Japanese Industrial Standards in Japan. History of semiconductor device development. Cat's whisker detector. Semiconductors had been used in the electronics field for some time before the invention of the transistor. Around the turn of the 20th century they were quite common as detectors in radios, used in a device called a cat's whisker developed by Jagadish Chandra Bose and others. These detectors were somewhat troublesome, however, requiring the operator to move a small tungsten filament around the surface of a galena or carborundum crystal until it suddenly started working. Then, over a period of a few hours or days, the cat's whisker would slowly stop working and the process would have to be repeated. At the time their operation was completely mysterious. After the introduction of the more reliable and amplified vacuum tube-based radios, the cat's whisker systems quickly disappeared. The cat's whisker is a primitive example of a special type of diode still popular today, called a Schottky diode. Metal rectifier. Another early type of semiconductor device is the metal rectifier, in which the semiconductor is copper oxide or selenium. Westinghouse Electric was a major manufacturer of these rectifiers. World War II. During World War II, radar research quickly pushed radar receivers to operate at ever higher frequencies, and the traditional tube-based radio receivers no longer worked well. The introduction of the cavity magnetron from Britain to the United States in 1940 during the TZID mission resulted in a pressing need for a practical high-frequency amplifier. On a whim, Russell Olive Bell Laboratories decided to try a cat's whisker. By this point they had not been in use for a number of years, and no one at the labs had one. After hunting one down at a used radio store in Manhattan, he found that it worked much better than tube-based systems. Ole investigated why the cat's whisker functioned so well. He spent most of 1939 trying to grow more pure versions of the crystals. He soon found that with higher quality crystals their finicky behavior went away, but so did their ability to operate as a radio detector. One day he found one of his purest crystals nevertheless worked well, and interestingly, it had a clearly visible crack near the middle. However, as he moved about the room trying to test it, the detector would mysteriously work, and then stop again. After some study he found that the behavior was controlled by the light in the room. More light caused more conductance in the crystal. He invited several other people to see this crystal, and Walter Brattain immediately realized there was some sort of junction at the crack. Further research cleared up the remaining mystery. The crystal had cracked because either side contained very slightly different amounts of the impurities Ole could not remove, about 0.2%. One side of the crystal had impurities that added extra electrons and made it a conductor. The other had impurities that wanted to bind to these electrons, making it an insulator. Because the two parts of the crystal were in contact with each other, the electrons could be pushed out of the conductive side, which had extra electrons, and replaced by new ones being provided where they would flow into the insulating portion and be collected by the whisker filament. However, when the voltage was reversed, the electrons being pushed into the collector would quickly fill up the holes, and conduction would stop almost instantly. This junction of the two crystals created a solid-state diode, and the concept soon became known as semiconduction. The mechanism of action when the diode is off has to do with the separation of charge carriers around the junction. This is called a depletion region. Development of the diode. Armed with a knowledge of how these new diodes worked, a vigorous effort began to learn how to build them on demand. Teams at Purdue University, Bell Labs, MIT, and the University of Chicago all joined forces to build better crystals. Within a year, germanium production had been perfected to the point where military-grade diodes were being used in most radar sets. Development of the transistor. After the war, William Shockley decided to attempt the building of a triode-like semiconductor device. He secured funding and lab space, and went to work on the problem with Brattain and John Bardeen. The key to the development of the transistor was the further understanding of the process of the electron mobility in a semiconductor. It was realized that if there was some way to control the flow of the electrons from the emitter to the collector of this newly discovered diode, an amplifier could be built. For instance, if contacts are placed on both sides of a single type of crystal, current will not flow between them through the crystal. However, if a third contact could then inject electrons or holes into the material, current would flow. Actually doing this appeared to be very difficult. If the crystal were of any reasonable size, the number of electrons required to be injected would have to be very large, making it less than useful as an amplifier because it would require a large injection current to start with. That said, the whole idea of the crystal diode was that the crystal itself could provide the electrons over a very small distance, the depletion region. The key appeared to be to place the input and output contacts very close together on the surface of the crystal on either side of this region. Brattain started working on building such a device, and tantalizing hints of amplification continued to appear as the team worked on the problem. Sometimes the system would work but then stop working unexpectedly. In one instance, a non-working system started working when placed in water. Ole and Brattain eventually developed a new branch of quantum mechanics, which became known as surface physics, to account for the behavior. The electrons in any one piece of the crystal would migrate about due to nearby charges. Electrons in the emitters, or the holes in the collectors, would cluster at the surface of the crystal where they could find their opposite charge floating around in the air. Yet they could be pushed away from the surface with the application of a small amount of charge from any other location on the crystal. Instead of needing a large supply of injected electrons, a very small number in the right place on the crystal would accomplish the same thing. Their understanding solved the problem of needing a very small control area to some degree. Instead of needing two separate semiconductors connected by a common, but tiny, region, a single larger surface would serve. The electron emitting and collecting leads would both be placed very close together on the top, with the control lead placed on the base of the crystal. When current flowed through this base lead, the electrons or holes would be pushed out, across the block of semiconductor, and collect on the far surface. As long as the emitter and collector were very close together, this should allow enough electrons or holes between them to allow conduction to start. The first transistor. The Bell team made many attempts to build such a system with various tools, but generally failed. Setups where the contacts were close enough were invariably as fragile as the original cat's whisker detectors had been, and would work briefly, if at all. Eventually they had a practical breakthrough. A piece of gold foil was glued to the edge of a plastic wedge, and then the foil was sliced with a razor at the tip of the triangle. The result was two very closely spaced contacts of gold. When the wedge was pushed down onto the surface of a crystal and voltage applied to the other side, current started to flow from one contact to the other as the base voltage pushed the electrons away from the base towards the other side near the contacts. The point contact transistor had been invented. While the device was constructed a week earlier, Brattain's notes describe the first demonstration to higher-ups at Bell Labs on the afternoon of December 23, 1947, often given as the birth date of the transistor. What is now known as the PA-Na-P point contact germanium transistor operated as a speech amplifier with a power gain of 18 in that trial. John Bardeen, Walter Hauser Brattain, and William Bradford Shockley were awarded the 1956 Nobel Prize in Physics for their work. Origin of the term transistor. Bell Telephone Laboratories needed a generic name for their new invention. Semiconductor triode, solid triode, surface states triode, SiC, crystal triode, and iotatron were all considered, but transistor, coined by John O. Pierce, won an internal ballot. The rationale for the name is described in the following extract from the company's technical memoranda, 26, calling for votes. Transistor. This is an abbreviated combination of the words transconductance, or transfer, and varistor. The device logically belongs in the varistor family, and has the transconductance or transfer impedance of a device having gain, so that this combination is descriptive. Improvements in transistor design. Shockley was upset about the device being credited to Brattain and Bardeen, who he felt had built it behind his back to take the glory. Matters became worse when Bell Labs lawyers found that some of Shockley's own writings on the transistor were close enough to those of an earlier 1925 patent by Julius Edgar Lilienfeld that they thought it best that his name be left off the patent application. Shockley was incensed, and decided to demonstrate who was the real brains of the operation. A few months later he invented an entirely new, considerably more robust, type of transistor with a layer or sandwich structure. This structure went on to be used for the vast majority of all transistors into the 1960s, and evolved into the bipolar junction transistor. With the fragility problem solved, a remaining problem was purity. Making germanium of the required purity was proving to be a serious problem, and limited the yield of transistors that actually worked from a given batch of material. Germanium's sensitivity to temperature also limited its usefulness. Scientists theorized that silicon would be easier to fabricate, but few investigated this possibility. Gordon K. Teal was the first to develop a working silicon transistor, and his company, the nascent Texas Instruments, profited from its technological edge. From the late 1960s most transistors were silicon-based. Within a few years transistor-based products, most notably easily portable radios, were appearing on the market. A major improvement in manufacturing yield came when a chemist advised the companies fabricating semiconductors to use distilled rather than tap water. Calcium ions present in tap water were the cause of the poor yields. Zone melting, a technique using a band of molten material moving through the crystal, further increased crystal purity. See also Integrated Circuit, VLSI, category, Semiconductor Device Fabrication, Thermal Processes in Semiconductor Technology, DLTS, Reliability, Hybrid IC, References, Muller, Richard S., and Theodore I. Kamins. Device Electronics for Integrated Circuits. John Wiley & Sons. ISBN A0-471-88758-7A.